Hello everyone. In this video we'll be studying the design of gasketed joints. So first we'll be seeing what are gaskets. Gaskets are actually an annular strip of material like washers which are used to obtain a leak-proof joint. So here first we'll be looking what is actually a joint with the leaks, then how these gaskets are helping us to achieve to obtain a leak proof joint. So in this figure you can see this one is actually a cylinder, so you can get a better isometric view here. So this cylinder will be looking like this. So this is the cylinder part, only the half sectional view of this one is shown here, and it is the flange end. And this cylinder will be carrying in, this is the actually the circular portion, and here it will be carrying the high pressure fluid. So this will be filled by high pressure fluid, and the end of the cylinder will be closed by the cylinder head, and this cylinder and cylinder head will be joined by the different some number of bolts. So here in this figure you can see only two bolts which are coming at this cross section, but actually there are some number of bolts will be used to connect, that is coming all over this flange surface or all over this pitch circle diameter. So this is actually a joint that is formed with the use of bolts between the cylinder and cylinder, and we will be seeing this is not a leak proof joint and how it is not a leak proof joint. So if I am zooming or having a closer look onto this part, that means where this cylinder and cylinder head is making contact, then you can get a closer view. So at the interface, that is at the interface of this cylinder where the metal is coming, and at the interface of this cylinder head is coming, the surfaces are rough. That means if you are looking onto the closer view, then there will be the possibility of voids that may be present due to the openings formed by the surface roughness are more. So as a result, the high pressure fluid which is present may be having a chance to leak through this void, so it will be finally getting out, so that it is not a leak proof joint. So in order to obtain a leak proof joint, you will be using some material, the strip like material in between the cylinder and cylinder head, and that material is known as gasket. This are usually the copper or asbestos made gasket materials are used, and that will be seeing now how these gaskets are providing a leak proof joint. So in this figure you can see another material or an extra material that is coming in between this portion, that is in between the cylinder and gasket. So this will be something looking like this annular, the strip of material, and at this half sectional view is actually you are seeing here. So this is coming in between the cylinder and cylinder head, and along with that the bolted connections are coming. So if you are placing this gasket over this flange end of the cylinder, then this will be looking like this. The annular portion, half annular portion is only shown, that will be coming here, and the bolt are coming at this or through this bolt holes. So how this use of gaskets is providing a leak proof joint, you can see here. Earlier we had a closer view at the interface where the cylinder and cylinder head is meeting. So in between here an additional material called a gasket is coming. So whenever we are applying the force, that means whenever we are tightening with the screws, this will be, the gasket will be getting deformed in between this cylinder and cylinder head material. So this will be getting deformed means this deformation will be helping us to close all the voids or gaps that is formed between. So this gasket will be getting deformed, and this will be filling all the voids in between the cylinder and cylinder head space, so that this will be providing a leak proof joint. So the deformation of this gasket that fills all voids in between, and hence it will be prevent the flow of fluid along this one, or from this high pressure fluid inside the cylinder to outwards will be stopped, and that's how we are getting a leak proof joint. And so now we have to design this gasketed joint. That means we have to find the dimension of this bolt which are coming in this for connecting this cylinder and cylinder head with the help of gasket. So actually we are designing this the dimension, or we are finding the dimension of this bolt which are used in this gasketed joints. So now let's get into the procedure or the design procedure of this bolts. So for designing these bolts, we will have to evaluate the stresses or the loads which are coming on the bolt. So here the load acting on the bolt may be calculated in two ways or in two steps. One is the stresses, or you can call it as load due to initial tightening, and the load due to the external loads, or the stresses due to external load. So we'll be calculating what is the initial tightening load acting on the bolt, and then the external load acting on this bolt. So we'll be seeing one by one here. So first we'll be evaluating the stresses due to initial tightening, or actually here we are evaluating the load or the initial tightening load we are seeing, and finally we will be converting this load to stress. So here you are seeing this gasketed joints where cylinder, gasket and cylinder head is there, and in between this the bolts are there. So first there is no fluid is in between, only the assembly is made, and you will be tightening the nut and bolt to make the initial assembly. So whenever the tightening load is applied, this tightening load will be creating a tensile load on this bolt and a compressive load on this gasket. So whatever be the tensile load acting, that same will be the compressive load acting on the gasket. So if you are calling this Fi is the tensile load on bolt, then the compressive tightening load on gasket will be equal to minus Fi. So here in data book an expression is there to find the initial tightening load, that is Fi. It is given in equation 9.1c. So it is given in terms of Fi equal to 2805D, where here it is mentioned as S units, but actually this equation should be read like this. So Fi is equal to 2805D newtons, where D to be substituted in mm. So if you are substituting this diameter, that is the diameter of this bolt, that is the major diameter of the bolt, then you will be getting in mm, then you will be getting the initial tightening load in newton. And the initial tightening load in this bolts are tensile, and that same load will be acting on this gasket, which are compressive. Here we are designing the bolt only, so we will be looking onto only or focusing only onto this load acting on the bolt. So this is the load acting on the bolt due to tightening. Next we will be evaluating the load acting on the bolt due to the external load. That means what happens when you are filling this space with the high pressure fluid. So that fluid will be creating external load on this bolt used. So we'll be seeing that now. So now here we will be seeing, or we'll be having this high pressure fluid filled between this or within this cylinder. That pressure of the fluid will be taken or represented by this small p, and the bore diameter of this cylinder used will be taken as capital D. So if that means this pressure will be acting over a cross-sectional area that is shown like this, and this area you can find it as pi by 4 into d square, where capital D is the bore diameter of the cylinder. So this pressure into this area will be creating the external load, or this load will be actually trying to separate this joint. So now this joint is formed, and you are inserting or you are filling this with the high pressure fluid. So this fluid will be creating this force that is given by Fe, which is the external load, P into pi d square by 4, and this will be trying to separate the load. So this load is to be withstood by all this bolt and gasket locations or joints. So here you can call this Fe is the total externally applied load, and this externally applied load is created due to internal pressure, and that value you can call it as P into pi d square by 4, where P is the internal pressure of fluid and capital D is the diameter of cylinder. If you are substituting in this one in SI unit, that means P in Newton per meter square and D in meter square, or P in Newton per mm square and D in mm, then you can get the value in Newton. So here we will be getting the total externally applied load only. But if there are n number of bolt, then we will be evaluating the load taken at a single bolt and gasket location. So that load we will be evaluating now. So we have the total externally applied load, that is P into pi d square by 4, and we are calling it by Fe. But actually the external load acting or taken at a single bolt and gasket location will be evaluated if you are using n number of bolts. Already mentioned, here you can see the 2 bolts, but actually the flange end will be coming like this, and the bolt, different bolt numbers you can count like this in this half portion, and same will be coming here also. So there may be 6, 8 or 12 number of bolts will be there. If n is the number of bolt in the assembly that is used, then you can evaluate the external load taken by a single bolt as the Fe divided by n, where n is the number of bolt, and you will be calling this as Fa. So this is the net external load acting at a single location of bolt and gasket. and from this one next calculation will be made. So this is the external load acting on both the a single bolt and gasket, and some amount of this load will be taken by bolt and remaining will be taken by gasket, and we need the part of load taken by the bolt for calculations, and that part of the load, how much part of this FA is taken, and that will be represented by a factor called a gasket factor. So we'll be seeing that factor now. So we have a factor called a gasket factor, which is represented by capital K. So we have already explained up to this point where FA is the net external load taken at a single bolt and gasket location, that is by FE by N, and a part of this FA taken by bolt will be evaluated with the help of this gasket factor. So this gasket factor is usually varying from 0 to 1. If gasket factor is 0.5 means the part of load taken by bolt will be equal to 0.5 into FA. So this will be of tensile nature as it is trying to separate the joint. So this will be of tensile nature, and the part of the remaining part of this external load FA will be taken by the gasket, and that you can obtain 1 minus capital K into FA. I will be showing all the equations or the required equations. So the we need only this part, that is the part of the external load taken by the bolt, which is K times FA, where K is the gasket factor, and we while solving problems we have to take that gasket factor from the design data book, and that we'll be seeing now. So we already determine the load acting on the bolt due to two reasons. One is due to the initial tightening and other one is due to this external load. So now we will be combining both of this load to find the net load acting on the bolt. So here you can see the net load on the bolt due to two reasons. One is due to initial tightening and another one is due to the external load, and already we have seen that this initial tightening load is represented by Fi, which is given as 2805D, where D to be substituted in mm to obtain this value in Newton, which is of tensile nature. And just before we have seen the FA is equal to FE by N, the load divided by number of bolt, where FE is equal to pressure into pi d square by 4. So now we are having that expression, and out of this gasket factor will be multiplied. So this is the part of the load taken by this bolt, and now you can this is also of tensile nature. So now you can combine this one to find the net load acting on the bolt. So that will be equal to F equal to K into FA plus Fi. So you can see this expression in this page 128 in data book in equation 9.2, that is given here. F equal to the final or net load acting on the bolt in gasketed joints, which is equal to F equal to, which is the net load, equal to gasket factor K into FA plus Fi, where Fa you are already knowing, Fa is the external load acting on this bolt. And you can obtain this gasket factor from this table 9.1 based on the different gasket materials. So in this one, the type of gasket materials are given. So if asbestos is coming in, then gasket factor value should be 0.6. If soft copper gasket is used, usually the common material used or that are coming in our problem are this soft gasket material, then this should be as 0.5. So you can obtain this gasket factor from this table 9.1. So if you are knowing this Fi and this K from this table, you can obtain the net load, that is capital F as K into Fa plus Fi. So using this one, you can find the dimension of the bolt, and that we will be seeing now. So to find or select the suitable bolt, we will have to evaluate the stresses. So stresses on the bolt will be equal to the net load acting on the bolt divided by tensile area. We already mentioned in the last video that the bolt stresses will be evaluated at the weakest section, and that is across the or based on this tensile area. So you can rewrite this net load acting on the bolt as K into Fa plus Fi divided by A suffix T, which is the tensile area. And this stress should be lesser than or equal to allowable tensile strength of this bolt material. So based on this one, you can find this value of 80 or the tensile area, and you are already having this tensile area from the data book, which you can select for a suitable isometric thread, and you can finally specify this thread like M12 or M14 like that based on this tensile area. I have already shown that corresponding column in the last video, and in next video based on these equations we will be solving a problem for this design of gasketed joints.